So let us look now to the implementation of the regular consensus that we described in the previous unit on the fail-stop model with perfect failure detectors. Alright, so let's have a look. So here is the implementation, and it is event-based, as we know. So if the consensus gets a propose from its application layer, and if it did not have any proposal yet, then it adopts this proposal. So this is basically setting the node's initial proposal until it has already adopted another node's proposal. This event describes what happens if this node is the leader. So it is saying if the rank of this node is equal to the value of the local variable round. It means if I am, say, process P3 and I'm in round 3, then I should be a leader. And this one is saying if I did not yet broadcast my proposal, because I should only broadcast once, and this says, if you just don't see this is not equal, just if you don't see it. So this says if I have a proposal, so we have the three things. Now I am the leader, I didn't broadcast yet, I have a proposal, then I will mark that I have already broadcasted now. I mark this, and then I will decide on my current proposal. This is clear. Decide permanently, and then I will trigger a web broadcast telling me that I have decided this is my round, and this is which is the proposal ID or number, and this is the proposal. Okay. What happened with other nodes? Other nodes, if they get a delivery of that message, so this is the ID or the proposal ID, and this is the proposal value itself. So if R is higher than my last proposal, then I adopt this proposal. Okay, so this is the proposal I adopt, and this is my last proposal number that I have. And also I say here that I got a delivery of a message at round R. And now this code is the code we need to move to the next round. Every node will move to the next round under the following condition. This is a restricted implementation. If it detects that the current round leader has crashed, this is round is element of detected. This is done by the failure detector, which I did not describe here. I'm just describing the core of the algorithm. The failure detector is working as usual. Whenever it detects a process, it added to the detected set, and it is a perfect failure detector. So either this will happen, or the leader is correct and it web broadcasts, therefore you will get a delivery of a message. This means that I got a delivery of a message from, in this case, then I can move now to the next round. So move to the next round if deliver or crash. That's what this is. Okay, so let's look at the correctness. Validity says one of the proposed values should be decided upon, and we can see from this algorithm we always decide either on own proposal or an adopted proposal, and this is a proposal from another node in the system. What about integrity? Rounds increases monotonically, and a node only decides once, and it decides in the round when it is the leader, and then after that it ignores everything. Okay, that is fine. What about termination? So the observation is that every correct node will make it to the round it is a leader. That's the most important. It is a leader, and once it is there, it will decide. Okay, how can this happen? Because if a previous leader fails, then by the completeness of our perfect failure detector, this node will detect it and go forward. And if the leader is correct, then by the validity of a BEP broadcast, which says if the sender is correct and the receiver is correct, the receiver will get the message, then the delivery is given. Now let us look to agreement, which says that no two correct nodes decide differently. The observation here is simple, is that the value to be decided upon will be the value of a correct node, which will be a correct leader, with a minimum ID. The first one, when we're going, that is correct, is the one that's really, the value it has at this round will be the one that will be decided upon. So take a correct leader with minimum ID. Because of termination, we know that this node will decide on a value V. It could be its own value, it could be an adopted value. It doesn't matter. It will decide on a value V because we have proved termination. What it's going to do now in this round, it will broadcast the value V. So every correct node gets V, if it is the leader, and will adopt this value. Okay, so because this was the first correct leader, because it has the minimum ID, the first correct leader. Okay, so every correct node will get V and adopts this value. And we know that all the nodes with an ID lower than this one are nodes that have failed. So, but we also know that no older proposal can override this proposal because of the proposal number scheme that we have. And if that is true, all future proposals will have the same value. And that is give us the agreement property. Before we continue, we can look to this issue or this question: how many failures can we tolerate here? In fact, this algorithm was a perfect failure detector. Is very resilient. It can tolerate up to n-1. So if we have 10 nodes, 9 of them can fail, but we still, the consensus will terminate and a decision will be made. So it's very fault tolerant. And the fault tolerance comes because of the failure detector. So we will see later when we have weaker failure detectors, we are not that resilient as here. So let us look to the same algorithm, but formulated in a different way. So the code that you see here is a code for process PI. It is formulated in a control-oriented notation. Let me explain the most important things about code. So this is a process PI. So as you can see, it just executes sequential code. And some of these code will be sending message. This is corresponding to sending message in a BEP broadcast. And then it has this funny construction, which is something called collect from a node. Collect from a node is basically an abstraction. A process executing here will wait on this collect from a node statement until it either gets a value, this is the value it gets from node R, or it detects the failure of node R. If it detects the failure of node R, the collect will return false. If it gets the message, the collect will return true. Okay, so now let us read the behavior of PI. PI starts with its own proposal, and then it goes in rounds, from round 1 to round n. And this code is executed if it is the leader. If the round is equal to my ID I, then I am the leader. So what should I do? I will propose the value, the current value of xi, and I will decide on this value, and I will broadcast this value to all nodes in the system. Decides, and this decide means actually exit from this loop. So it decides and it terminates the for loop here. And all messages coming to this node, then it will be ignored from that on. If it is not the leader, it will wait for a message. If it gets a message and it will get a message from the leader of that round. If it gets a message, it will adopt this message. It's basically how it is. It will adopt this message, and it will not move to the next round until it adopts this message. So in a sense, the code here is saying cannot go ahead so quickly. The node will wait until it gets a message in round I, whatever that round is, let's say round 5, or it gets a failure of the leader of round I, round R, let's say. Okay, good. So that is the code for in a control-oriented fashion. It's a very compact code. It needs the abstraction of collect, of course, to work, and it does not go quickly around. So it waits in a round. It has to get that message. It buffers all other messages for rounds later, and this collects specifically for a message from node R or a failure detection of node R. What about uniform consensus? In the control-oriented notation, uniform consensus is very simple, extremely simple. Instead of deciding here, we decide at the end. We don't decide here. We decide until we go through all the rounds. And by this, any decision made in previous rounds will be actually collected, and at the end, everybody has the right value. Okay. Thank you.